Hello students. In the previous class, we had discussed about homomorphism and isomorphism. So isomorphism is if you have a function f from g to g dash, and if it is a homomorphism, and also f satisfies 1, 1 and onto function, then we say that f is an isomorphism. So in this class, we'll be seeing some theorems and problems based on isomorphism. So let us look at the first theorem. Let f from g to g dash be an isomorphism. Then f of e is equal to e dash, where e and e dash are identities of g and g dash respectively. And the second one is f of a inverse is equal to f of a the whole inverse for all a belonging to g. And the third one is order of a is equal to order of f of a. So in the previous classes, we had already proved the first two cases in case of f being an homomorphism. So the same proof can be applied here as well. If you have to modify, then this is a modified form of the proof. So you have, it is given that f is an isomorphism. So you consider let a dash belong to g dash arbitrarily. Since f is an 1, 1 and onto function, there exists an a belonging to g such that f of a is equal to a dash. So we have a is equal to ea is equal to a, as g is a group, and a and e belongs to g. This implies f of a is equal to f of ea, that is equal to f of a. Since f is a homomorphism, I can write this as f of a into f of e. This is equal to f of e into f of a, which is equal to f of a. So f of a is nothing but a dash. So you have a dash into f of e, that is equal to f of e into a dash, that is equal to a dash. You've got back the same element after you multiply that with a dash with f of e. So f of e is the identity in g dash, and I denote that by e dash. Next one. So we need to prove that f of a inverse is equal to f of a the whole inverse. For that, I can take a inverse is equal to a inverse a, that is equal to e. Applying f on all the sides, because f is a 1, 1 function, it is well defined. I can write it as f of a inverse is equal to f of a inverse a, that is equal to f of e. Using the definition of homomorphism, I can write it in this order, and therefore conclude saying that f of a the whole inverse is equal to f of a inverse for all a belonging to g. Now the third one. So we need to show that order of a is equal to order of f of a. So here there are two cases, order of a being finite and order of a being infinite. So let us look at the first case. Let a belong to g and order of a is equal to m. I have taken order of a to be a finite quantity. If I say order of a is equal to m, then m is the least positive integer such that a to the power m is equal to e. This is a definition of order. So this implies f of a to the power m is equal to f of e. You have a to the power m. A to the power m can be written as a into a into a m times. Since f is a homomorphism, I can write it in this order. So this implies f of a multiplied m times is f of a to the whole to the power m is equal to f of e, where f of e is the identity element of g dash. So this implies order of f of a should be less than or equal to m, because order of any element is the least positive integer which satisfies order of f of a is equal to some quantity, and that quantity will be less than or equal to m. Any value greater than m may also satisfy this condition. So we are checking the least positive integer which satisfies this. So I take this as order of f of a is less than or equal to m. So I take let if possible order of f of a is equal to k less than m. So order of f of a is equal to k means I can write this as f of a whole to the power k is equal to f of e. So f of a whole to the power k is, you're multiplying f of a k times, and since f is a homomorphism, I can write it as f of a into a k times. So this becomes f of a to the power k, that is equal to f of e. Since f is 1, 1, a to the power k is equal to e. This is showing that order of A is equal to K, which is less than M, which is a contradiction since order of A is equal to M. So order of f of A cannot be less than M. Hence, order of f of A is equal to M, that is equal to order of A. So when order of A is finite, we have shown that order of f of A is also finite and both are equal. If suppose order of A is infinite, we need to prove that order of f of A is also infinite. So if suppose order of f of A is finite, I'm taking the contradictory. If suppose order of f of A is finite, then as proceeded above, as explained in the earlier proof, we get that order of A to be finite, which contradicts the hypothesis that order of A is infinite. Hence, order of f of A is also infinite. So if order of A is infinite, then order of f of A will also be infinite. So in both the cases, order of A is equal to order of f of A. So whenever you have f to be an isomorphism, order of A will always be equal to order of f of A. Now let us look at some of the problems based on isomorphism and kernel. So show that the additive group r comma plus of all real numbers and the multiplicative group r plus comma dot of all positive real numbers are isomorphic under the mapping defined by f of x is equal to e to the power x for all x belonging to R. So by data we have f from r comma plus to r plus comma dot defined by f of x is equal to e to the power x for all x belonging to R. So to show it is an isomorphism, we need to prove that it is a homomorphism 1, 1 and on 2. So to prove it is a homomorphism, I first take f of x plus y because the operation here is plus and whereas operation here is dot. So this is f of x plus y is equal to f e to the power x plus y, and by law of exponents we have it as e to the power x into e to the power y. So e power x is nothing but f of x, e to the power y is f of y. Therefore we have f of x plus y is equal to f of x into f of y. Therefore f is a homomorphism. Next we need to show that f is 1, 1. So for that we consider let f of x is equal to f of y. This implies e power x is equal to e to the power y. This implies you're multiplying e to the power minus y on both the sides. So we have this as e power x minus y, that is equal to e power y minus y is nothing but 0. So e power 0 is 1, where 1 is the identity element of r plus comma dot. So this implies x minus y is equal to 0. Since e power x minus y is equal to e to the power 0, we are equating the powers. So you'll get, since the bases are the same, you can equate the powers. So this becomes x minus y is equal to 0 or x is equal to y. Therefore f is 1, 1. So we need to show that this f is an onto function also. So we already know that inverse of an exponential is logarithmic and inverse of logarithmic is exponential. One is the inverse of the other. So let y belong to r plus. So there exists log y belonging to r such that f of log y is equal to e to the power log y to the base e. This is nothing but this is equal to y. So for every y, you can find a log y in R. For every y in R plus, you can find log y in R such that f of log y is equal to y. Therefore, f is onto. For every value, you get a pre-image because it is only positive real numbers. So log of positive real numbers definitely exist. Hence, f is an isomorphism. Similarly, let us look at the next example. Let z comma plus be the additive group of all integers and h is equal to minus 1 comma minus 1 be the multiplicative group. I am defining a function f from z to h as f of z is equal to 1 if z is even, minus 1 if z is odd. So all the even numbers are mapped to 1, all the odd numbers are mapped to minus 1. So we need to show that F is a homomorphism and find out what is a kernel, and we have to check whether F is an isomorphism. So to prove that F is a homomorphism, there are different cases here. The cases being, you take any two numbers Z1 and Z2. So we need to show that F is a homomorphism. That is to show that F of Z1 plus Z2 is equal to F of Z1 into F of Z2, because here in Z the operation is plus, whereas in H the operation is multiplication, that is dot. So F of Z1 plus Z2 is equal to F of Z1 into F of Z2. That's what we need to prove. But we have different cases, being that Z becoming an even or odd. So case 1, if both Z1 and Z2 are even, then Z1 plus Z2 is also even. Therefore, F of Z1 plus Z2 is equal to, since it is an even number, Z1 plus Z2 will be equal to 1. F of Z1 plus Z2 is equal to 1. Now, F of Z1 is equal to 1 as Z1 is even, and F of Z2 is also 1 as Z2 is also even. So, my product of these two is equal to 1. Therefore, we can say that F of Z1 plus Z2 is equal to F of Z1 into F of Z2 in this case, the first case. Second case, if Z1 and Z2 are both odd, then F of Z1 plus Z2, Z1 plus Z2 becomes an even number. When you add two odd numbers, you get an even number. So F of Z1 plus Z2 is equal to 1, whereas F of Z1 is equal to minus 1 and F of Z2 is equal to minus 1 as Z1 and Z2 are odd. So product of the minus 1 and minus 1 becomes 1. Therefore, F of Z1 plus Z2 is equal to F of Z1 into F of Z2. The third case is Z1 is even and Z2 is odd. Or you can take the other way around also. Z1 is odd and Z2 is even. You get the same answer. Then Z1 plus Z2 is odd. You add an odd number with an even number, you always get an odd number. So therefore, F of Z1 plus Z2 is equal to minus 1. Here, F of Z1 is equal to 1 and F of Z2 is equal to minus 1, because Z1 is even and Z2 is odd. So product of 1 and minus 1 is equal to minus 1. Therefore, we have F of Z1 plus Z2 is equal to F of Z1 into F of Z2. Since in all the three cases this satisfies, we say that F is a homomorphism. So the next thing what we have to check is what is the kernel of F. And kernel of F is given as, kernel of F is defined as all those elements Z belonging to Z such that when you map these elements using F, that should be mapped to an identity element. So kernel of F is equal to Z belonging to Z such that F of Z is equal to 1, as 1 is the identity element of 1 comma minus 1 under multiplicative group. So since 1 is the identity of H, we get this as kernel of F is equal to Z belongs to Z such that F of Z is equal to 1. So when is F of Z equal to 1? F of Z is equal to 1 if Z is even. So kernel of F contains all even integers. Now F is not an isomorphism because F is not 1, 1. Since F is not 1, 1, it is not an isomorphism because all even numbers are mapped to 1 and all odd numbers are mapped to minus 1. So they are not a 1, 1 function because two or more values in Z are having the same image. So this is how you find the kernel of the function F. Next one, show that F from G to G defined by F of X is equal to 2 power X is not a homomorphism. What about its kernel and is F an isomorphism, where G is the multiplicative group of non-zero real numbers. So by data we have F of X is equal to 2 to the power X. So F of Y is also equal to 2 to the power Y. Now we consider it is a group under multiplication. So we need to consider F of XY. So F of XY is equal to 2 to the power XY. But we have F of X into F of Y is equal to 2 power X into 2 power Y. This is equal to 2 power X plus Y. So from these two we have F of XY is not equal to F of X into f of y. Therefore, f is not a homomorphism. Since f is not a homomorphism, kernel of f is not defined, and also f is not an isomorphism. Always remember, only if f is a homomorphism, you can find kernel of f. Next example, f from Z8 to Z2 is given by f of x is equal to r, where r is the remainder when x is divided by 2. So all the elements of Z8 are mapped to Z2, and r is nothing but r is f of x is equal to r, and the function is given by f of x is equal to r, where r is a remainder when x is divided by 2. Show that f is a homomorphism. Find kernel of f. This is given as an exercise for yourself, because we have already proved this one, the second example. Under the same basis, you do this also, f from Z8 to Z2. Consider even numbers and odd numbers and show that this is a homomorphism, and similarly find kernel of f. So if you've done with this example, take a photo and post it in the comment section where I post this video. Thank you.